So begin with a word of prayer to get up here. Dear Father, we thank you for this day again. I thank you for these students in this class, and just ask that you bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So I think I probably should start with a couple of just like basic limit examples. So these are examples which won't require, no need for L'Hopital's rule. So we'll start with a few examples in that category, and then I'll transition and state L'Hopital's rule again, and we'll start doing some bunch of examples with that, all right? So let's start out relatively simple, but in other sense relatively complicated. Limit as x goes to infinity of x to the 13th power plus x squared minus 7 divided by, let's say, x to the 14th power plus 3x cubed minus 10. All right? So this is an ambiguous limit because as x goes to infinity, we've got infinity upstairs and we've got infinity downstairs, right? Can you guys tell me what the limit is? What's that? Infinity? I've got to vote for infinity. Any other votes? Any votes for 1? 0, 10, pi, e, natural log of 2? No? All right. Well, let's see here. What we're going to do is we'll divide the top and the bottom by x to the power 14. So what is x to the 13th over x to the 14th? Right, 1 over x. So that's why I get 1 over x here. And then plus 1 over x to the 12th minus 7 over x to the 14th divided by 1 plus 3 over x to the 11th, I think. 14 minus 3 is 11. And then minus 10 over x to the 14th, right? So at this point, I have rewritten the limit in such a way that we can see what the limit works out to, right? Because now I can apply laws of limits. And I get 0 plus 0 plus 0 divided by 1 plus 0 plus 0, which of course is equal to 0 over 1, which is also known as 0. The answer here is 0. As a general rule of thumb, if you have a larger degree in the denominator than the numerator, then you can divide by the highest power in the denominator, and this kind of calculation will go through, right? Just a generic point of order. If you're taking the limit as x goes to infinity, and the denominator polynomial has a larger degree than the numerator, the limit's 0, right? We've kind of seen this before when we talked about the graphs of rational functions, right? We have a horizontal asymptote of y equals to 0 if the denominator polynomial is larger degree. Let's see another example. How about if we have the limit as x goes to infinity of 3x to the 4th plus x squared minus 2 divided by, 2x squared plus 3x plus 1. How would you do that one? Well, again, if we divide by the highest power in the denominator, it should actually reveal the nature of the limit here. So we got limit as x goes to infinity, divide the top and the bottom by x squared. We get 3x squared plus 1 minus 2 over x squared divided by 2 plus 3 over x plus 1 over x squared. So as you look at this limit, what's the only thing that really, what dominates the limit? right? It's fairly obvious that the thing that wins, the thing that is the dominant behavior as x goes to infinity is this term, right? Because it gave us this. And everything else here goes to what? Like, 1 minus 0, or this goes to 2. So you've got something huge, plus 1, divided by 2. We get something huge. So yeah, the limit here is infinity. And so as a generic point of order, if we have the ratio of two polynomials, if the degree of the numerator is larger than the degree of the denominator, then the limit goes to infinity, right? If the denominator has a larger degree, the limit goes to 0. What happens if they have equal degree? That's kind of the other case, right? So example 3, I'll put it here. What if you had something like the limit as, and we'll do minus infinity for a change, minus infinity of 13x to the 132nd power plus x plus 2 divided by, I don't know, 39x to the 132nd power plus x squared minus 42. All right, so again, just divide by the highest power in the denominator, and what do you get? Well, you got the limit as x goes to minus infinity of 13 plus x over, excuse me, plus 1 over what? 1 over x to the what? 131st power. X over x to the 132 is 1 over 30, x over 131. 1 over x, this, I can't say it, plus 2. I'm glad we have symbolic algebra these days. There was a time when math had to be done in terms of English prose, or Latin prose, worse yet. Like long sentences explaining the formulas. Isn't it nice we don't have to do that? X to the power 2 and so forth and so on. And then downstairs, we've got 39 plus 1 over x to the 130 minus 42 over x to the 132, just to give you a ridiculous example. Everything there, except for the leading terms, dies to 0, right? So we can just straight calculate the limit with the limit of the quotient as the quotient of the limits which exist, which in this case gives us 13 plus 0 plus 0 divided by 39 plus 0 plus 0, also known as 13 over 19, or 1/3. Yeah, very good. So that's the third case. So the three cases, if you have the ratio of two polynomials, either the denominator has a larger degree, it goes to 0 as x goes to plus or minus infinity. If the numerator has a larger degree, then as x goes to plus or minus infinity, you either go to plus or minus infinity depending on the sign of the most large term. It could go plus, it could go minus, Like if instead of having a plus 3 here, I'd had a minus 3, this limit, for example, 2 would have been minus infinity, right? And then if the degree of the numerator and the denominator are equal, then the limit as x goes to infinity or minus infinity is just the ratio of the leading coefficients, right? Now, so it's good for you to be able to show the steps that I just did, right? But it's also totally acceptable, especially in the context of a larger analysis, to just write down the answer. All right, these are things you're allowed to memorize in here. Now let's do something a little bit harder. What if we have the limit as x goes to minus infinity, all right, of, let us say, x divided by the square root of x squared plus 2. So you guys tell me about this. What do you think the limit should be? Isn't the denominator kind of like an x? Like the square root of x squared, isn't that x? And the top is x, right? So the limit should be what? X over x, right? Which is what? It's 1, right? Okay, if that's right, let's try plugging in minus 100 into this, see what happens. What's minus 100 divided by the square root of minus 100 quantity squared plus 2? What do you get? You get the square root of 10,002, which is roughly 100. This is approximately minus 100 over 100-ish, which is -1. So what's wrong with what I just tricked you guys into believing? I didn't have to work hard because this is already a misconception that is popular. The square root of x squared is x is not true. I repeat, the square root of x squared is not equal to x. The square root of x squared is equal to the absolute value of x, which is equal to plus or minus x, depending on the context. And the context here is that x is negative, right? X is negative because we're taking the limit as x goes to minus infinity, so that's the problem. So this is a popular mistake, like the square root of x squared is x. And it's usually okay because oftentimes we're in the context that x is positive, right? If we're in that context, that's okay. But if we're not, it'll make you wrong. So it's a little bit, so that's why I say this one's, in your homework I have one that I say be careful. I'm talking about this issue, okay? So like here, if we do limit as x goes to minus infinity, and what we need to do actually is do divide by minus x above and below. So like x over minus x divided by minus 1 over x square root of x squared plus 2. See, because really, let me just do the math over here. Minus 1 over x, of course, is 1 over minus x, which, by the way, is 1 over the square root of x squared for x less than 0. So if I do that, I have the limit as x goes to minus infinity of minus 1 divided by, well, that's 1 over the square root of x squared times the square root of x squared plus 2, right? And then we do have a property that the square root of a times the square root of b is the square root of a times b, right? That's a property of the square root function, provided you're feeding it positive entries. Okay, so limit as x goes to minus infinity. We got minus 1 over the square root of 1 over x squared times x squared plus 2, which is the limit as x goes to minus infinity of minus 1 over the square root of 1 plus 2 over x squared. At this point, we've resolved the limit, right? Because now you can just you can think about taking the limit as x goes to infinity. It should be clear now what happens, right? The 1 over x, the 2 over x squared, this guy goes to 0, right? And what you got is just minus 1 over the square root of 1 plus 0, also known as minus 1. And that's why we numerically found minus 1 when we plugged in minus 100, right? So I told you guys this before, I'm telling you again. You have calculators, you can check your work. If you're dealing with a limit at infinity or minus infinity, it takes you just a second to plug a big number into the expression to see what happens, right? Double check your work, yeah.
So if this was going to x goes to infinity, would the answer be 1?
Yes, if it was going to infinity, the answer would be 1. Exactly. Very good, yeah. Yes, sir. Yep, yep. The graph of this is, yeah, go ahead.
Oh, remember, I got to think of how to phrase my question.
Take your time. I think this is tricky, right? This is tricky. That's why I'm showing you, not just leaving it on the homework for you to not notice and then kind of not see it. Now, Dr. Joseph told me he accidentally put this on a test in Calc 1. Like, I was talking to him last semester, and he inadvertently put this particular, not exactly this problem, but this issue accidentally popped up on his test. Like, oh, he wasn't trying to trap the students. It just happened accidentally, you know, and it's just there. So maybe this is your question, like, what's the deal?
I was gonna say, would that be true for if x was like a higher exponent, say it was like to x cubed or like x?
Good. That's a very great question. I was hoping you're going there. So it's an even-odd issue. So here's the deal. So like the nth root of x to the n is just equal to x if n odd. But the nth root of the nth root of n is equal to the absolute value of x if n is even. So what's going on, roughly speaking, is this: is if you graph x to the n for odd, this is basically y equals x to the n odd, right? So in that case, it's a one-to-one function, and there's an inverse function, which is the nth root function. So like this means that when I compose the nth root function with the nth power function, I get back where I started, right? That means that the composition of the nth root function and the nth power function is the identity function. In other words, the nth power function and the nth root function are inverses. That's possible because for the odd power, it's a one-to-one function. It passes the horizontal line test. It has what we call a global inverse. In contrast, when I graph this guy for n even, I don't have a global inverse. All right. See, I have to do a different thing for positive and for negative. I can just go on the one side and I can have a one-to-one function if I just go positive. I can have a one-to-one function if I just go negative, but I can't have it for both positive and negative. And that's reflected in this identity. So just watch out. It's basically odd powers are super nice. Even powers, they're trying to get you. And irrational powers of a negative number, you should just be like, no, sir, that's not in this course. What are you doing? That's a Math 331 question. That's not a Math 131 question. All right, enough of this. Just wanted to give you guys a quick, review of algebra stuff. Let's talk about L'Hopital's rule, sometimes called the hospital rule, because I think L'Hopital is basically hospital in French. I don't know. There seems to be disagreement about the spelling, but we're going to call it L'Hopital rule. And like I told you guys last time, if the limit of f over g is type 0 over 0 or infinity over infinity, then the limit of f over g is equal to the limit of f prime over g prime, provided they exist. All right. Actually, this also still holds in the case that they're divergent sometimes, but there are examples where it doesn't quite. I'm just saying be careful in the divergent case. All right, so anyway, we're going to focus on the case that it works. Let's see here. So let me give you a quick proof, first of all. This is not in the notes, and this proof is it's really a partial proof because this assumes a very special case, and so here it goes. Limit as x goes to a of like f of x over g of x. Let us assume that we're dealing with type 0 over 0. And let's assume that both of the functions are continuous. What would that mean? I mean, they better be continuous if you're going to differentiate them at the limit, you know? Anyway, let me not get too carried away with my side comments here, because honestly, guys, the full statement of L'Hopital's theorem is technical, and there are like a lot of cases here. So if the f and the g are both continuous and it's type 0, 0 over 0, what does that mean f of a is equal to and f of g has to be equal to? You know, we got the limit as x goes to a of f of x equals to 0. We've got the limit as x goes to a of g of x is equal to 0, right? What does that mean? What is f of a? If f is continuous, that is equal to f of a, right? That's our continuity. It's equal. The limit of the function is the value of the function at the limit point. So by continuity of f and g, we should have that, right? So I can take this and I can rewrite this, no cost to the student, f of x minus f of a over g of x minus g of a, right? Because those are 0. How can I turn those into derivatives? What do I do? Quotient rule, not quite. How would you, remember we talked, how did we define the derivative? We defined the derivative in terms of the limit of the difference quotient, right? How about if I divide the numerator by x minus a and I divide the denominator by x minus a, right? If I do that, and then I use the quotient rule for limits, the limit of the quotient is the quotient of the limits, what do I have? I'll get out of the way here in a second. This is a good review for the final, right? Because you guys have forgotten about the derivative's definition from the limit at this point, right? Fondly in the past. Some of you know, you're like, I want to get back to limits. I love limits. Please, more limits all the time. No? No, you guys never said. So what do we have? We've got, that's f prime of a, right? And that's g prime of a. Do you guys agree? So that's f prime of a and g prime of a. And of course, that is, of course, equal to the limit as x goes to a of f prime of x over g prime of x, which is L'Hopital's rule. The thing that makes this a really partial proof is, like, it doesn't have to be the case that the derivatives at the limit point actually exist to do L'Hopital's rule. This is like a very, I would say this is a cheesy proof. It's not really. It doesn't really prove the rule in any of the cases we ever use the rule. So but it does give you some kind of sense of why this rule is true, at least. So it's worth a minute of our time. So there it is. All right, so let's get into the L'Hopital examples then. Unless you guys have a question about something in particular. Did I ever move the camera over there? I think I did. So I don't think, by the way, guys, that the first 4 examples I did today are helped by L'Hopital's rule. I don't think L'Hopital's rule really is a good tool to calculate the first 4 examples. The first 4 examples are what they are. And while it's true, the first 3 I probably could do with L'Hopital's rule if I was really patient. It's just better to do those with algebra in one step rather than, I don't know, 142 steps. So example, where are we? 5? Example 5. So here's a famous one. We worked this out before by the, the squeeze theorem. So limit as x goes to 0 of sine of x over x. What would that be equal? Well, we know it's equal to 1, right? We proved that before. Maybe we put an h there. Limit as h goes to 0 of sine h over h is equal to 1. We proved that by a squeeze theorem argument based on a picture in the unit circle. That was important to the proof that the derivative of sine was cosine, right? But now we could apply L'Hopital's rule if we forgot this limit, right? We could remember it. We could derive it with L'Hopital's rule. So this is type 0 over 0. What's the derivative of sine? Cosine, all right. And what's the derivative of x? 1. So this is equal to cosine of 0 over 1, also known as 1. So if you, for some reason, forgot what the limit of sine x over x is, we can easily derive it with L'Hopital's rule, right? Recognize this does not prove this limit, right? Why is that? That would be a very circular argument. Because in order to do this limit, I have to differentiate cosine. I have to differentiate sine, right? But the very derivation of the derivative of sine assumes this limit. So like it doesn't give you a proof of this limit. Unless you want your logic to be circular. Which I guess is popular sometimes. Mostly politicians, though. Let's see here. So, example 6. What if we look at the limit? I'll do one of these. Limit as x goes to infinity of like x squared plus 3x plus 2 over 2x squared minus 7. So if I apply L'Hopital's rule, well, first of all, you shouldn't even, I mean, technically speaking, if you believe what I told you earlier today, you should be able to tell me the answer already, right? What should the answer be here? Ratio of the leading coefficients, right? Which is what? 1/2. Let's work it out with L'Hopital's rule just for the sake of the experience. So if we differentiate the numerator, we get what? We get 2x plus 3. Differentiate the denominator, 4x. Right? That's still type infinity over infinity. So L'Hopital again. Yeah. So, and not everybody uses this notation, guys. This notation was taught to me by Dr. Lane of Appalachian State University. Dr. Lane was a great guy. He helped me out a lot. He worked for NASA before it was NASA. The dude was so skinny, I swear you could have fit him through like a basketball hoop. But he was a great guy. He was funny. The students in front of his class were like inviting us to come to like some kind of liberal fundraiser on campus or something, and Dr. Lane was like, I'm a conservative, could I still come? It's like, it's just funny. Anyway, helped me do an independent study of Calc 3 over the summer. He was a good guy. So limit to half like we predicted. Example 7. So here we have the limit as x goes to infinity. Did I ever move the camera? I can't remember if I did. So we're looking, let's see here, I think it's limit as, oh yeah, I did. This is why I can never win games of memory. Limit as x goes to infinity of natural log of x squared divided by the cube root of x. How do you guys think we should, first of all, what type of limit is this? Is this an indeterminate form? What are the indeterminate forms? Do you guys remind me? I'll help you out. 0 over 0? Infinity over infinity? What are the others? The next two are 0 times infinity. Infinity times infinity just blows up. That one That's not indeterminate. That just blows up. That one's easier. 0 times negative infinity. So when I say 0 times infinity, I mean to include like plus or minus infinity there, but that's good, that's good. So infinity minus infinity is the other common indeterminate form. There are also indeterminate powers. 0 to the 0, 1 to the infinity, infinity to the 0. These are all indeterminate forms as well. There are basically 7 common indeterminate forms. And we can use L'Hopital's rule to try to attack any of these, and we will. At the moment, we're focusing either on 0 over 0 or infinity over infinity, so let's continue. We could just apply L'Hopital's rule here if you guys like. See what happens. Want to try it? All right, so L'Hopital's rule, this goes to infinity, that goes to infinity. So we've got limit as x goes to infinity. I differentiate the top, I get 2x over x squared. Differentiate the cube root, I get 1/3 x to the minus 2/3. And now I need to clean that up, right? So what do I got? X goes to infinity of 2x times x to the 2/3 divided by, oh wait a minute, that's a 6. 6 x squared. I guess, I mean, I could have left the x to the minus 2/3 downstairs if you want, like whatever. What's the net? What do we have here altogether? 6x to the what? Well, let me think about this. So upstairs we have what? Upstairs we have x times x to the 2/3, which is what? X to the 3/3 plus 2/3 is 5/3. How many thirds do we have downstairs? X squared is 6/3, right? So you got 5/3 upstairs, you got 6/3 downstairs. So the 6/3, they cancel out and you're just left with 6 over x to the 1/3. So the limit is? Yeah, 0. The other thing you could have done here to start with, and you know, maybe this would have made it slightly easier, is you could have traded this for a limit as x goes to infinity of like 2 times the natural log of x divided by the cube root of x, right? And then you could have gone from there. It wouldn't have really made it much easier, but that's another way you could have gone here. Use laws of logarithms before you do the L'Hopital's rule, okay? Shall we do another? Let us try another. Let's do one that looks like 0 times infinity. Oopsie. All right, here we go. So this one is the limit, where am I? Example 8. So here we have the limit as x goes to 0 from the right of x times e to the 1 over x. So up to this point, we've been able to just apply L'Hopital's rule because we already had a fraction, right? But this is not like this. This is type, this right here is type 0 times infinity, right? Because e to the 1 over x goes to e to the, what happens to 1 over x is x goes to 0 from the right. It goes to infinity, right? And e to the infinity is infinity again, because the exponential gets really, really big for large values. So I need to convert this to a fraction. How do you convert a product to a fraction? Think about it like this way. If I've got a times b, how do I rewrite that as a fraction? I kind of only have two choices. I can either do a times 1 over b, or I could do b times 1 over a. Or what else could I do? That's pretty much it. I mean, that's kind of our go-to trick here. So I think I want to make the x go to the denominator. So to do that, I have to reciprocate the x in the denominator. That's a trick. So e to the 1 over x divided by 1 over x. Now that's a kind of weird algebra step, right? That's probably not an algebra step that you have made in the forward direction. Like, you've simplified stuff like this before, right? But you haven't deliberately, mangled an algebraic expression to make that happen. But now we have a reason to do it, all right? Because the reason is, if you can rewrite the expression as a fraction, where the limit of the functions involved is either 0 over 0 or infinity over infinity, then we can apply L'Hopital's rule. So then what? Is that what we want? What type is it now? The top goes to infinity. The bottom, what happens to? We're taking the limit as x goes to 0, right? So limit as x goes to 0 there. The 1 over x goes to infinity, right? If in doubt, draw a graph, right? What's 1 over x look like? Y equals 1 over x is this thing, right? So as x goes to 0 from the right, that goes up to infinity, Or if you like, just think about plugging in a really small number into 1 over x, right? You get 1 over something really small is something huge, right? Okay, so now we can do L'Hopital's rule because we've got the right kind of pattern. So limit, L'Hopital's rule, infinity over infinity. Okay, so I get limit as x goes to 0 from the right. What's the derivative of e to the 1 over x? Well, it's e to the 1 over x times the derivative of 1 over x, which is minus 1 over x squared. And then what's the derivative of 1 over x? Well, it's minus 1 over x squared. Well, that's wonderful because we've got a minus 1 over x squared above, and we've got a minus 1 over x squared below. They cancel, right? And we get what? Right, e to the 1 over x. And what's that limit? Yep, that is infinity. So this one blew up. Man, some of these markers smell like death. I don't know why is like, no. Not good. Do you ever have those scented markers when you were little? Yeah, they do smell kind of terrible, don't they? Let's see here. All right, so here's another example, kind of like example 8. Example 9, this is a popular example. Limit as x goes to infinity of e to the minus x times x squared. So again, what happens as, what does e to the minus x look like? What's the graph of e to the minus x? It's this, right? What happens as x goes to infinity? It goes to infinity, right? My bad. I'm a dummy. I'm sorry. I've gotten things twisted. It goes to what? As x goes to infinity, e to the minus x goes to? Not infinity. What? No. Just 0, right? E to the minus x goes to 0 as x goes to infinity, right? What does x squared do as x goes to infinity? infinity, right? So what are we looking at? Yeah, this is type 0 times infinity again, all right? So you got two choices. You can either move the exponential to the denominator, or you can move the x squared to the denominator. I strongly suggest leaving x squared right where it is, because I would much rather differentiate x squared than differentiate 1 over x squared, you know? Because when you differentiate 1 over x squared, it differentiates to 1 over x cubed, which is kind of worse. Unless you've got some kind of fortunate coincidence like this one, where that, you know. So here, but you really have two choices. So you try something, and if it doesn't work, you dust yourself off and you try again. Somebody should make a song. I see here, e to the x. There we go. X squared over e to the x. That's just algebra, right? And now we've got type infinity over infinity, so we can apply L'Hopital's rule. Let us do such. Limit L'Hopital's rule, type infinity over infinity. Limit as x goes to infinity of 2x over e to the x. I have used the quotient rule 0 times in this lecture. Please let that sink in. L'Hopital's rule, you differentiate the numerator, differentiate the denominator, you divide those derivatives, right? You don't actually have to do the quotient rule, because we're not differentiating the fraction. We're applying L'Hopital's rule, which is a theorem. Oh man, it's still infinity over infinity. So what do? Again, exactly. So L'Hopital's rule a second time. And we get what? 2 over e to the x. What's the answer? 0. Yep. And I think, let us, you know, can you guys see what's the story here if we generalize this example while we're at it? What would happen if instead of having the second power here, what if instead of having the second power I had like the nth power, e to the minus x times x to the n? It would still be 0, you know, by like n applications of the L'Hopital's rule. And here I'm assuming, you know, n a positive integer. If n was negative, that would be a different story. Or would it? That might still be true, actually. Actually, I think if n is negative, it's just automatic. It's just clearly 0 without L'Hopital's rule. If n is negative, that means you're looking at 1 over, like if n was negative, if you had something like e to the minus x times x to the minus 3, for example, that would just be 1 over x cubed times e to the x, right? So like if n is negative, I don't even need L'Hopital's rule. It's just manifestly clear that that's 0. And if n is equal to 0, it's just the limit as x goes to infinity of e to the minus x. So actually for any integer n, this limit's 0. You could work it out. Let's see here. So as a generic point of order, a nice slogan to remember is that exponential growth beats polynomial growth, right? So the exponential, I mean, that's essentially what we're weighting here is exponential growth versus polynomial growth, right? In a battle of exponential growth versus polynomial growth, the exponential wins, all right? So it just grows way faster. Eventually. And the limit as x goes to infinity is all about eventuality as opposed to what happens in the finite case. Here's another one. Example 11. Here we've got the limit as x goes to infinity of x squared over the natural log of x. So now what am I doing? I'm comparing apparently exponential growth, I'm comparing polynomial growth to logarithmic growth, right? That's what's going on in this example. What do you think is going to win? Logarithmic or polynomial? Which grows faster? I think you're right. I think polynomial is going to win. Let's work it out. L'Hopital's rule is the hammer to hit this nail with, right? I mean, All right, so I think it's already infinity over infinity, right? So we can apply L'Hopital's rule from the outset. No kind of algebraic trickery needed. And so we got ourselves limit as x goes to infinity of 2x over 1 over x, which is the limit as x goes to infinity of 2x squared, also known as infinity, right? So yeah, apparently the x squared won, right? So the next example will deal with infinity minus infinity. We haven't hit that yet, so let's look at that. Here we're looking at the limit, example 11, rather 12. Here we're looking at the limit as theta goes to 0 from the right of cosecant theta minus cotangent theta. All right. So I guess I probably should remind you guys, cosecant is 1 over sine theta, and cotangent is cosine over sine theta, right? So both of these functions have a division by sine theta. What happens with sine theta as theta goes to 0? Well, it's 0, right? So we've got division by 0 for both of these formulas. So this is type infinity minus infinity. It's important that it's just from the right, I think, because if I make it from the right, it's unambiguous. Like from the right, this is going to infinity. From the left, this goes to minus infinity. Because from the left, we'd have sine as a little bit negative. And so you'd have like 1 over a really, really small negative number, which would be like minus infinity. And then I think this, but I think the other one, but actually it's like from the right, it's infinity minus infinity. From the left, it's like minus infinity plus infinity. So either from the left or the right, this is the same kind of like difference of infinity limit. So kind of like your question about minus infinity times 0. Like we would say minus infinity plus infinity and infinity minus infinity, it's the same indeterminate type, right? Anytime you've got a difference of something that's stupidly large and positive against something that's stupidly large and negative, that's an infinity minus infinity type limit. So how should we deal with this? I think this is the answer is almost right here, right? Just write down the definitions in terms of sine and cosine and see if you can do algebra to start with. What do we got? One over sine? Yeah, cosine theta over sine theta. It looks like we've already got a common denominator. It's just waiting there for us to use, isn't it? So limit as theta goes to 0 from the right of 1 minus cosine theta over sine theta. Right? And this is kind of what usually happens for this kind of limit, is you make a common denominator, and what's going to happen when you do that is it's going to switch the infinity minus infinity to like either a 0 over 0 or an infinity over infinity kind of limit, I think. I think it's usually infinity over infinity. Well, no, this is 0 over 0, right? So the top goes to 0 because we get 1 minus 1. Cosine of 0 is 1, right? So we get 0 over 0. This is type 0 over 0, which means we can apply L'Hopital's rule. So here we go. L'Hopital's rule this time type 0 over 0, and we got ourselves a limit as theta goes to 0 from the right. What happens when we differentiate 1 minus cosine? We get what? Yeah, sine. Yep. Minus a minus sign, which gives a sine, right? And then the denominator, we get a cosine theta. And we're done. Because you can just plug 0 into that, right? That's tangent, in fact, and but I'll write it this way. That's sine of 0 over cosine 0, which is also known as 0 over 1, also known as 0. And so you're like, wait a minute, you're telling me that infinity minus infinity is 0. I knew that already, right? Don't be deceived. That's a coincidence. Like it just happened here. It doesn't have to happen that way. All right? If you have type infinity minus infinity, it is possible for these things to work out to anything. That's why they're called indeterminate. It just so happens this one works out to 0. Don't view it as a license to simplify other ones to 0 automatically. I hope the next example doesn't work out to 0. Let's find out. Let's see here. So this one, we've got example, what am I on, 13? So we've got the limit as x goes to 1 of 1 over the natural log of x minus 1 over x minus 1. What is the natural log of 1? Nobody knows? No, natural log 1 is not 1. So you guys should have a mental picture of natural log. Like the graph of natural log should be in your mind's eye. I think that, at least for me it is. I don't know. That's how I think. So like this is the graph of natural log. And so like this point right here is 1, 0. See, 1, 0 is the x-intercept of the log function. So log of 1 is 0. Log of something a little bit left of 1 is negative. Log of something a little bit to the right of 1 is positive. So the 1 over natural log is either going to minus infinity from the left or plus infinity from the right. Conversely, the 1 over x minus 1 function, right, what's that? You got your vertical asymptote at x equals to 1. It's the reciprocal function shifted 1 unit to the right, right? That's y equals 1 over x minus 1. So as you can see, again, we've got plus infinity from the right, we've got minus infinity from the left. So if you look at it, from both sides, you either got infinity minus infinity, or you've got minus infinity minus a minus infinity. In other words, both sides, it's type infinity minus infinity. So what should we do? What should we do? I've made my case. It's type infinity minus infinity. So how do we proceed? Yeah, you guys aren't just going to leave me hanging here, are you? No ideas? Combine the fractions. I were like, okay, so how would we do that? Excellent. That's exactly what we should do. So let's do it. So we have the limit as x goes to 1. And just like you told me, x minus 1 minus the natural log of x, all divided by x minus 1 times the natural log of x. I think this is the first example we've had where the differentiation wasn't just dumb. Right? Like the differentiation here actually makes me have to stop and say, oh, wait a minute, I gotta be careful. Right? I gotta be careful because I've got a product rule in the denominator when I differentiate the denominator. But before I do that, can I apply L'Hopital's rule now? Is that reasonable? This goes to what? 0 minus the natural log of 1, which is 0. This goes to 1 minus 1 times the natural log of 1, 0 times 0. I think we're good. It's type 0 over 0. So, like I told you guys, make a common denominator, it's going to work for us. So 0 over 0. Now the derivative of the top function is pretty easy. It's just 1 minus 1 over x, right? Let me use a different color for the dividing line here. All right. Now downstairs, I have the derivative of the first thing, which is 1. So I get log x plus x minus 1 times 1 over x by the, I'm doing the product rule on the denominator. Well, the numerator is still type, the numerator limits to 0. And it looks to me like the denominator also limits to 0. So we're still type 0 over 0. I think that I don't think I just want to do L'Hopital's rule again here. It might, well, maybe that will work. I'm not sure. Let me just do one algebra step before we differentiate, okay? So the algebra step I'm going to do. So in my mind, guys, let me know. I'll tell you my thoughts. My thoughts are maybe I should multiply this by x over x. Maybe that would be helpful. Maybe not. I don't know. But 1 minus 1 over x. Downstairs, I've got log of x. And so I get plus 1 minus 1 over x, all right? Oh, I like this. I think this is going to be okay. Let's do L'Hopital's rule again. We can do that because we still have type 0 over 0, right? So L'Hopital's rule again. And so as a general point of order, guys, if you're not sure, usually what I usually do, if I'm not sure, is I do L'Hopital's rule again. And then I take a second and I think about my life and I think about, is this going in a good direction? Do I want to still continue pursuing this option, right? And I think it's going to work out okay here. So what's the derivative of the numerator? Well, it is 1 over x squared, right? Because minus a minus gives us a plus. Right? Do you guys see that? The derivative, x to the minus 1 power, I differentiate it. I get a minus 1, x to the minus 1, which is minus 2. But the minuses cancel. So I get that. Downstairs, I got a 1 over x, and then plus 1 over x squared. Oh, sweet. We're done. I should have just forged ahead, you know? Look, I promised. Infinity minus infinity is not always equal to 0. This time it's equal to a half. Right? That is why these are called indeterminate forms. It's because you don't know what they're going to work out to until you get through it, you know? Any questions? Yes, no, maybe so. Nobody? All right. I'm going to do the indeterminate powers tomorrow. I'm not going to start that right now because I think I don't want to break your brains, you know, enough new stuff for one day, right? But I do want to do some more examples that might be helpful to you. So I want to do more examples of the same type. And here's a nice one. The limit. So if you've seen the announcement, I hope you've seen the announcement. I announced which problems are collected from the next homework, because one of you kindly reminded me yesterday to do that. And thank you so much for doing that, because I forget. And anyway, so I picked out a list and I posted it in the announcement. And that might seem like a long list, but I hope you noticed that a lot of those are L'Hopital's problems, right? L'Hopital's problems, like a lot of them are just kind of like, beep, we're done. Every so often though, watch out, there are some L'Hopital's problems that are like